So a very brief intro, guys, because you've seen some of this before. This is my AI program running on the PC. It has got internet access, but it's not running on, it's not a big AI. I'm not running ChatGPT. It's called the Minstrel one, which I've downloaded. So it's running locally on my graphics card here, which is, what is it, 5070, I think it is. But I don't need all that power for it. It runs in C on C++ under Ollama, but the coding of the actual AI, which is here, which you can download yourself and try it if you want to. I've got it on my page. It's all done in Python. So what I'm going to show you today is autocode running. What I had before, but you've not seen that either, is I can get it to generate Python code, which it detects and puts in the second window. It comes up in the main window and then it puts it in here, and then I could manually run it. But I decided, although that was pretty quick, I decided what to do was, if I run it, and it was quite common with these kind of not so good AI chat bots type things, if it makes mistakes, you have to sort of copy them and paste them in and say you made a mistake, fix it. I thought, well, I'll just get it to any mistake to put it back into the input text box like feedback, and then it can see its mistake and then correct itself. This is something we used to say back in the 70s when we were students. I remember a friend of mine who was a computer science student, I was an engineering student, he used to say, he was from Birmingham. He used to say, well, the computer comes back and it says syntax error, you made this mistake here. Well, if it knows what the error is, why the hell can't it just fix it itself? So it's essentially what it's doing here is if you give it the error, then it can fix itself and it'll rewrite the code, and it'll keep doing that, and hopefully till it gets right. But sometimes if you're not careful, it'll just go around an infinite loop if it can't fix it. Of course, you have to be careful doing that, that I suppose in principle it could improve itself as well, the AI, and that's the whole point of the exercise. You could get it to improve its own code, and I believe that is going on at the moment as we speak. There's some United States or China are probably working on that. It's not so dangerous as you might imagine, because you're going to be using a special computer to do it on, so if it messes things up, you just sort of reload and start again. But here I've got this thing here. If I don't put that on, then it doesn't work automatically. So if it suddenly decided to take over the world, as long as that button's not on, that checkbox, then I'm okay. So I put that on, then it does it automatically and it goes round in a loop. The rest of it doesn't matter. So you can see the model I'm using, a Minstrel 3, which isn't that old. It's a French model, and it came out in about, I don't know, it's a couple of months ago, maybe, I don't know. Can't remember now. It's also got vision on it. I think you've seen some of the vision work before on my YouTube videos. So let's just get down to some examples and showing you how it works. So I'm going to put the auto code tick box on. If I didn't, I can manually press the button, but it should do it directly from a speech command without that. And if there's any mistakes, I should hopefully auto correct them. Sometimes it makes mistakes because the library's been changed, and then we'd have to do an internet search to find out how it's been changed, if it's using any libraries. Put the auto run on. Write code to show a 3D model of a sphere.
Python code ready, code block.
Wow, that's incredible. When it works really well. There's the Python program, no mistakes at all this time. And it just, well, of course, it's probably quite a standard thing to do. Just to see if we can do a circle.
I can see your 3D sphere visualization has been successfully generated and saved to C:4.
That's it, just saying it's been successful. Write Python code to produce a circle.
Python code ready, code block.
Write Python code to produce a Mandelbrot set. Wow. There it is. It's the classic Mandelbrot set, the chaos thing. I remember doing that about 30 years ago on an old Apollo computer in Paisley to while the hours away during the summer. So anyway, so it can do that quite easily. Let's get it to do a mathematical thing. Now I'm going to get it to do a calculator. So it's going to be write code to make a scientific calculator. Make sure it is aesthetically pleasing. Use tkinter Windows for the user interface. See how it handles that. Put it on auto run again, so it should self-correct if it gets it wrong. And for some reason it's actually searching the internet. I don't know why it's doing that, but be interesting to see what it comes up with nevertheless. It's looking through Python group geeks for geeks. It's looking up scientific calculator. It's going to nick one off the web. Just wait. Interesting that it's doing that anyway, so let's just wait and see what it comes up with. The searches do take a little bit of time. Oh my god, there it is. Whether it works is another matter. 3 plus 2. Goodness, it works. Okay, I'm going to make it harder for it now. I'm going to change it to a scientific calculator. Let's hope it won't search the internet again. Write more code, but this time make it a scientific calculator. See what it does there. My goodness. I'm flabbergasted. Divided by 2. Oh, it's missed out the equal sign, I think. Okay, let's try it on a Butterworth filter. I've got show code as to how a Butterworth filter works. Use a sine wave as an example. And I've got the auto code thing on. So it should correct itself. And if it makes a mistake, you should be able to see it correcting itself. Let's see how it works. I'll just type it in this time. Hope it's not going to search the internet again. No, it's not. It's not this time. It's going to do it itself. So Windows should appear here. There it is. My God, that was quick. Oh, That's not so good. Oh, wait a minute. So the filtered signal, there's the original noisy signal, and the filtered signal, and the original, that's the spectrum. The filtered spectrum, oh I see, yeah, so that's the noise reduced. That's amazing how quick that was. I have tried it before and it wasn't so successful. It didn't even make a mistake at all that time. There's the Python code. Okay, let's try again. Put the auto run on so that it corrects any mistakes it makes in the code. And this time I'm going to do, oh, that's the wrong thing. So I'm going to say show Python code to find the dB frequency response of a second order system with a variety of damping factors from 0.5 to 1.8 and undamped natural frequency 100 radians per second. See if it manages that. So the auto code's on, so it should correct if it's wrong. It makes a mistake. Oh, got it right first time. We just got the auto scaling wrong. The looks of it, it's truncated it for some reason. So just telling it to auto scale. I don't know if it's what's done that. That's a bit better. Yeah, that previous one was kind of cut it off. I don't know exactly what it did, but that plot's better. Should be minus 40 dB per decade. Here's a decade, 10 to the 2 to 10 to the 3. It should go from just 30, should we go to 70? Yeah, there it is. So it's minus 40 dB per decade. Looks right. That should be around 100. Sorry, a square root of 100, which is 10. So a very long time ago, seems like 100 years ago almost, for my PhD I was working on areas related to Wiener filters and Kalman filters. So I'll give it a question here. Write code for a simulation of a Wiener filter showing colored noise and additive white noise. Show the original colored noise signal, its estimate, and show the signal plus noise on a separate graph. Hope it gets that right. So these are random signals. Oh, put the auto run on just in case. It's not making many mistakes anyway, surprisingly. Yeah. So the code window should appear. I don't have to manually do it. Just run, so it's basically running the code itself. Oh, there it goes. No mistake. Oh my goodness. I'll just try and get that all in. So there's the original colored noise, random signal. There's the signal plus noise. So it's this guy with white noise, and then this is its estimate. So these guys should be close, which, well, they are. Like they are. We could graph them both on top of one another. I could say it makes a hell of a change from MATLAB, doesn't it? You know, having to just with a prompt getting it to do the simulation for you. These are MATLAB type plots because it's using the MATLAB kind of simulated library which Python's got. Let's just do this. Let's say repeat the previous command, but show the original signal and estimate on the same graph. You see it's not a little bit squashed together there. Anyway, let's go. Put that away. That's the old program. Should produce. Oh, there we go. Magnificent. So there's the signal plus noise, colored signal plus noise. And here you can see the green signal is the Wiener filters. Even it's a lovely way it's presented, isn't it? And the blue one's the original colored noise. That the green one's its estimate, and that's what you're measuring. That's the signal plus noise. Show the code for an amplitude modulated signal and take the Fourier transform to show the spectrum. There's a different way of entering the speech recognition dictation mode. Made a mistake there. Oh, I got it right second time. Not a very good graph of the AM, but you can see that's very good how it's done that. There's the carrier and the two sidebands. Obviously, that's 10 hertz. The signal, the carrier is at 50 hertz, and it's a very basic signal processing thing. So important part of that demo was that it made a mistake in the code and it corrected itself automatically. Let's do the following. Put it onto auto run and into dictation mode. Put white noise through a coloring filter so that it's band pass filtered, and then take the Fourier transform of the output and display both. That should do. So put white noise through a coloring filter so that it's bandpass filter so it becomes color noise, and take the Fourier transform with the output and display both. I hope it's going to understands what I'm saying there. Anyway, let's do it. Oh, that's fast, isn't it? So there's the bandpass. It understood what I was saying. There's the bandpass signal. It's not white noise, it's colored there, and then it's taken the output and it's taken an FFT, it's taken a Fourier transform centered around 150 hertz. It must be the bandpass. Yeah, so here you can see in the code it's put the lower and upper frequencies, breakpoint frequencies, 100 hertz to 200 hertz. So it's got a bandwidth of 100 hertz. The filter that it's passed it through, it's sampling at 1000 hertz. Okay, I mean it's not exactly that hard to do yourself, is it? But it's quite amazing that it can do it at all if you think back a few years. Fourth order polynomial. So I can actually use the plot function which I've got, which I put in as a different thing, not related. It's not running Python or anything. Show the equation on its own.
Here is the fourth order polynomial equation. Box px equals 2x to the power of 4 minus 5x cubed plus x squared plus 7x minus 4.
I'm going to plot that. I'm just going to manually do it. So it's got, with the looks of it, let's scale it down a bit. Y min, put that to, it's got 2 real roots out of 4. You can see there, it's really nice plotter, isn't it? And we can manually do that. You can see there's a root. Again, you can't see, it's gone off your screen, but here I can put my cursor on and see that it, oh, it's off the bottom. Anyway, I'll tell you that it's at minus 1.15, and that's the one root. The second root is 0.66. Okay, so what we'll do is we'll get it to write a program to work out the roots. Use that polynomial and write Python code using Newton's method to find the roots of the polynomial. Quite remarkable. I didn't expect that. That's exactly how it should be. That's the polynomial. Now, did it get the... Well, it's just sort of stuck on the... It hasn't given me the complex roots. So I'm saying here, explain what the Newton-Schultz method is as regards taking the inverse of a matrix and use it in a Python program to find the inverse of whatever. And this is a lower triangular matrix. It makes it very easy to find the inverse of it. Let's go. It's not going to give, made a mistake in the program. It's not going to give any audio out because I didn't put that on. So it didn't converge, it says. Oh, it's done it again. Oh, and it's done it. Second time. And a quick check on MATLAB, guys. Let's put that matrix in. It's a lower triangular, 2, 0, 0, 3, 3, 0, 4, 4, 4. And I use it because it's easy to recognize if it's right, because the eigenvalues of a lower triangular matrix are the diagonal elements. So the eigenvalues are 2, 3, and 4. So I know at least that the inverse is the reciprocal of those eigenvalues in that particular case. So you get 0.5, 0.33, and 0.25, and it's got 0 in that element and minus 0.33. And we look over here, you probably won't be able to see it, but that's exactly right. It's got this element here is 10 to the minus 11. It's that it's worked it out to be, so it's pretty close to 0, isn't it? And this one minus 0.33, it's got minus 3.33 times 10 to the minus 1. It's got all the other elements spot on, so that works. Got it right.